In this section, we're going to continue our discussion of techniques for finding the limit of a function at a particular point. And we're actually going to give these techniques a particular name. And we've seen some of this before. We've seen a situation where if we're taking the limit of a function which we know to be continuous, like here we want the limit as x approaches 2 of this expression. This expression is presumably f of x is equal to that expression, you see, and we know that this is a polynomial function and therefore its graph is continuous. And so all we need to do in order to evaluate the limit at a point is to make a substitution. Just replace x with 2 in this expression and evaluate. Let's do that. We have, let's see, 2 cubed would be 8, 2 squared 4, so minus 2 times 4 is minus 8, 8 minus 8 they go out, minus 5 times 2 is negative 10, negative 10 plus 6, negative 4. So negative 4 is the limit as x approaches 2 of this function. Now, here's one where we might be led to think that we have something funny going on here because we have a rational function. And we know that the graphs of rational functions sometimes involve vertical asymptotes. And if that's true, then if we're finding the limit as x approaches that point where the asymptote is, that vertical asymptote lies, then we're going to have a limit that doesn't exist. But here, notice that our asymptote, our vertical asymptote, will appear at the value of x that causes the denominator to become 0, and that would be negative 3. So if there is a vertical asymptote, and there may not be, but if there is, it would be at negative 3. But look, we're taking the limit at x as x approaches 2. So we're not approaching that funny point, you see, and the graph then is continuous in the neighborhood of this value. And so all we need to do is substitute to find the limit. All right, let's do that. We have 2 squared 4 plus 2 is 6. 6 minus 6, 0. So we have 0 in the numerator. In the denominator, we have, let's see, 2 plus 3, 5, 0 over 5, 0 for the limit. Here's a revisit of a problem that we looked at in the previous section. Now, this involves a technique that we're going to call cancellation. Now, we found this. We said the limit as x approaches 2 of this expression, and we evaluated this using a table of values and also by looking at the graph. And now we just want to approach it algebraically. Here's how the thought process would go if we're evaluating algebraically. We might think, well, let's see. One thing we might see is that 2 causes the denominator to become 0. 2 times 2, 4, minus 4, 0. And that we might think leads us to a vertical asymptote. Then again, maybe it doesn't. See, it doesn't always give a vertical asymptote. Now, to be able to tell, here's what you do. You evaluate the function, the expression here, at this target point 2 and see what you get. Because we're looking to get something that will tip us off to a certain technique. F of 2 means replace all these x's with 2's, and we have this, and evaluating we find 0 over 0. Now when you get this kind of fraction, 0 over 0, this is called indeterminate form, and it kind of means that this form of the function is a form in which we can't determine the limit. And this idea of zeros in numerator and denominator goes back to our study of polynomial functions. Remember we talked about zeros of functions? And that is a value of x which causes a numerator or denominator to become 0 can be thought of as a 0 of the numerator and denominator. And if we have zeros, it implies factors. So here we have zeros for the numerator and denominator for an x value of 2, and it implies that x minus 2 is a factor of both numerator and denominator. So we have a cancellation opportunity. So indeterminate form is given by this idea. When we evaluate the fraction, we get 0 over 0. We say this is indeterminate form, so we can reduce by using a cancellation. And that works by going through a factorization process. In the numerator here, for the same expression, we have this factored form. In the denominator, this factored form. The x minus 2's go out. So we have x plus 4 over 2. And now to find the limit of the original function, we can just take the limit of this form of the original function. Now, this is not the same function. I don't want to imply that they are identical to one another. This is a simplification of that. but they are not equivalent to one another exactly. And you can tell that they're not equivalent by looking at the graphs of those two. This graph is a straight line, and this graph is a straight line with a hole in it. You see, and at that one point, and it turns out to be the target point in our limit evaluation situation, but at that one point we have a hole in the graph. So the two expressions are not exactly identical, but we can use this simplified version of that expression to evaluate limit. That's the idea. So the limit as x approaches 2 for this expression would be found by substitution. So let's see, 2 plus 4, 6, 6 over 2, 3 is the limit of the function, as we found earlier. Here's another one. We're going through this process now of cancellation again, and you discover the need for cancellation by tripping over this indeterminate form, and you find that like this. If we want the limit as x approaches 1 of this expression, then what we do is evaluate this expression for 1. That is, f of 1 is, and I'll replace this x with 1, replace all these x's with 1's, and we get 0 over 0, implying the indeterminate form. Now, once we see indeterminate form, we know we have a cancellation opportunity with factors in numerator and denominator, and therefore we can evaluate limit using a simplified version of this. Okay, so we go back to this expression and factor. Now, I'm factoring in the denominator by using the method of grouping. Considering these two as a group, let's see, x squared is common to both of those, so I snag x squared out of those two terms. X squared out of this term leaves x. X squared out of this term leaves minus 1. And then I'm leaving this in its current form. There's no factorization opportunity there, but I do want to think about this as a binomial, because now I have these two terms. You see, I can think of it like that, as these two terms, and in those two terms I have the common factor x minus 1. So I pull x minus 1 out of this term and I'm left with x squared, pull x minus 1 out of this term and I'm left with an understood 1. So now the x minus 1's can go out, and I can find the limit of the original problem by finding the limit of 1 over x squared plus 1, which turns out to be, well, let's see, replace x with 1. We have 1 squared, 1 plus 1, 2 in the denominator, so 1/2 turns out to be this limit. Now, we need to keep in perspective this idea of the opportunity for cancellation. You have that opportunity when you discover this indeterminate form. And it isn't always the case that you're going to need to use this technique when you see that your target point is a 0 of the denominator. Some students think that that's your tip-off. No, your tip-off is to evaluate the function at the target point and arrive at 0 over 0 to determine that you have an indeterminate form, and then you go through that cancellation process. Take a look at this problem. This doesn't fall into that category. The limit as x approaches 2 means, well, let's see if we can just use substitution. We would have 2 plus 5, 7 in the numerator, 2 minus 2, 0 in the denominator. Oh, this fraction is undefined. Now, with an undefined situation like that, we know that the graph of this rational function happens to be one of those that's curvy, and we have a vertical asymptote at x equals 2. And this is that situation where the limit does not exist. Okay, so we come to that determination by looking at this. This is not the indeterminate form, even though the fraction is undefined. The indeterminate form is 0 over 0. Okay. Here's another one where we're going to use a technique of simplification in order to evaluate limit. But this time the technique for simplifying is rationalizing. Here's how we make the discovery for the need. The limit as x approaches 0. All right, so we would presumably evaluate f of 0, and we can just do that mentally here. 0 plus 1 is 1 under the radical. The square root of that 1 is 1. 1 minus 1, 0 in the numerator. And f of 0 here in the denominator would be 0 as well. So 0 over 0, indeterminate form. That gives us an opportunity for manipulation here in changing this expression to a new one which we can find the limit of rather easily. Now, the technique used here is rationalizing, but in our past experience we rationalized denominators, but here we're going to rationalize the numerator. That is, it's a technique for removing the radical from the numerator. And to do that, recall that if we're rationalizing and we have a radical involved and a binomial involved, that we multiply by the conjugate. Now the conjugate of this binomial is the same binomial with a different sign, so we're going to multiply in the numerator by the square root of x plus 1 plus 1. You see, this is the conjugate of that binomial. And then if we do that in the numerator, we need to do the same thing in the denominator because we're multiplying by a form of 1 to change the form of the fraction but not its value. So we have, let's see, the square root then of x plus 1 plus 1 downstairs. Parenthesis all around the binomials will help keep straight our multiplication. The square root of x plus 1 times the square root of x plus 1, we know that that's x plus 1 squared under the radical, so that gives us the radicand x plus 1. And then we know the middle term goes out in this process. When we're multiplying the difference of terms times the sum of the same two terms, we get the difference of squares, it turns out. Middle term goes out, we don't get a trinomial as the result. The last term is negative 1 times plus 1 or minus 1. And now in the denominator, it's just x times the binomial, which I brought down here. These 1's go out, so we have x over x times, and let me write it like this. I forgot my parenthesis. So we would have this, and then the x's would go out, and we have 1 over this binomial. And that's the simplified form that we can use to evaluate limit. So we evaluate it as the limit as x approaches 0 of this expression, and now we can use substitution. When x is 0, we have 0 plus 1, 1 under the radical. The square root of 1 is 1. 1 plus 1, 2 in the denominator, so 1/2 then is the limit of that particular function. Here's another problem involving indeterminate form. When we first look at the problem, we would make the substitution. We would replace x with 0 and make the discovery of indeterminate form. Now, if x is replaced with 0, we have 1/3 here, then minus 1/3, 0 in the numerator. And if this x is replaced with 0, we have the 0 over 0 indeterminate form. That just leads us to understand that we can manipulate whatever expression that we have here, and through that manipulation we can find the limit of the newly manipulated expression. You see, that's the idea. Now, the manipulation here, it kind of goes back to something that we've learned in a very early chapter, or maybe even in a previous course, but it's taking this and simplifying it using a common denominator. There are actually several ways to simplify this complex fraction. One way is to identify a common denominator among all of the little fractions involved. And that common denominator happens to be 3 times x plus 3. And then just multiply that common denominator into both this numerator and this denominator. You see, so really we're taking this expression and multiplying by a common denominator over itself, a form of 1 just for the manipulation purpose. All right, now it's this common denominator is multiplied times each of these fractions. You see, and the common denominator is multiplied times x in the denominator. One way to see the cancellations easily is to write the common denominator times each of these fractions. So I've written down here, common denominator times this fraction, and then minus sign, and then common denominator times this fraction. And then in the denominator, of course, we have 3 times x plus 3 times x, which is easily seen as 3x times x plus 3. But in the overall numerator, there's a lot of business to take care of. These x plus 3's go out, so we have 3 times 1, 3. And then the 3's go out here, and we have x plus 3 times 1. So it's minus x plus 3, or minus x minus 3. The 3's go out, and we have minus x in the numerator. Notice that I've left the denominator in factored form, and I suggest that you do that because you're always looking for cancellation opportunities, and you can see those more clearly if you're looking at factors. But at any rate, we have the x's canceling here, leaving negative 1 in the numerator over 3 times x plus 3, or that minus sign in the numerator can float to the position of the sign of the fraction. Well, now that we have simplified a bit, we can think about this as the limit as x approaches 0 of that expression negative 1 over 3 times x plus 3. And now, well, let's see, by substitution, replace x with 0, and we have in the denominator 3 times 3, or 9, so we have negative 1/9 then for that limit. Here's another one. This is interesting because we're not finding the limit of a function so much as we're finding the limit of an expression that is written in terms of a function. And the function is this little simple function, and the expression turns out to be the difference quotient. We studied difference quotient in an earlier chapter when we were first talking about functions generally and function notation. And here we're re-emphasizing the idea of difference quotient. Difference quotient comes up quite often in calculus, in the early studies of calculus, and we may have a chance to see it a little bit more in this course as well. But here's how we take care of the situation. We recognize this upon replacing h with 0. We recognize this as indeterminate form because, after all, if h is 0, we would have f of x here, then minus f of x. That's 0 in the numerator. And then when h is 0 here, 0. So 0 over 0, indeterminate form. That just tells us that we need to go through some kind of manipulation. The manipulation here is just the simplification of this expression using the information about the function itself. Now, all we're doing here is using what we know about function notation and what it means. So I have written the function up here. I just repeated it just so that we can look back at it a couple of times. Here's our difference quotient expression. And now what does it mean? Well, let's see. F of x plus h means in the f function, replace x with x plus h. So here's the f function, and here's the expression for it, and we're replacing the x with x plus h. So we have 3 times x plus h minus 1 for this. Now, for emphasis, I want to separate the idea of this part of the numerator and this part of the numerator. And I'm doing that with symbols of inclusion somehow. So in the brackets here, f of x plus h is this. Right? All it is this expression with x replaced with x plus h. That's all there is to it. Okay, then minus f of x means minus this. So it's minus, here's f of x. You see, and now we go through and simplify. We have 3 times x, 3x, 3 times h, 3h. Bring down the minus 1. This is minus 3x plus 1. And now a lot of things go out very quickly here. 3x minus 3x go out. We have minus 1 plus 1. They go out. So we have 3h over h for our fraction. The h's now go out, and we have a constant 3. So the situation becomes relatively trivial. Now we find the limit as h approaches 0 of the constant 3, and we know that that is simply the constant.